Hi, welcome to Viveka Physics classes, and in this particular video let us try to solve a JEE advanced problem from the chapter Electrostatics. Take a look on the problem. Okay. Okay. Here in this problem we have a positively charged ring on which there is a charge of Q which is uniformly distributed. The total charge on the ring is Q and radius of the ring is capital R, and now a point charge capital Q is placed at the center. Okay. Now they are asking three questions on this. The first one, find the increase in the tension in the ring after the point charge is placed at the center. Second question, find the increase in the force between the two semicircular part of the ring after point charge is placed at the center. Okay. Third question, using the result found in the part B, find the force that the point charge exerts on the half of the ring. Okay. But before that we find increase in the tension in the ring, first let us try to figure out why there is an increase in the tension in the ring. Okay. For that, let us try to divide this ring. Let us try to split this ring into small segments of small charge dq. Let me consider one segment here of charge dq. The charge of this is dq, and let me consider another diametrically opposite segment of the same charge dq, and we can consider n number of segments here on the ring, and each segment should be diametrically opposite. Okay, so here we have two segments. Okay, you can consider another two segments here diametrically opposite. Okay, I have considered n number of segments on the ring. Now according to Coulomb's law, we know that there should be an electrostatic repulsive force between the charge placed at the center and the charge of this small segment, and this electrostatic force will be acting in this direction, and I'll call this force as F or dF, you can call. Now the same force will be acting on this segment in the downward direction. Okay, and similarly the same amount of force will be acting in this direction on this segment, and in this direction on this segment, and in this direction on this segment, and the same force will be here in this direction on this segment, and here also we have a segment. Okay, now you can see the diagram. Each part of the ring is experiencing an electrostatic repulsive force due to the charge placed at the center. Now as a result of all these forces, the ring is said to be stretched. Okay, due to stretching of the ring, obviously the tension will be produced in the ring. As a result of this, tension in the ring increases. So now we got the idea why the tension in the ring increases. Now let us try to calculate the expression for increase in the tension in the ring. Okay. Okay. Now let me consider a small segment of the ring, very small segment. In the diagram it may look bigger, but in reality this segment what I am talking about, it is very small. Let us say this segment length is AB, length of this segment, arc length is AB, and this segment composed a charge of dq. The total charge that appear on this segment is dq. Okay, so here I have taken. Now let us only analyze this part. I'll draw the small part of the ring here little bigger, so that you can see complete resolution of all the forces on the ring. Okay, let us consider the positive charges, some certain amount of positive charges on the ring, small part of the ring. Okay. Okay, now I call this as AB length. Okay, the total charge on this is dq. Okay, this is radius and this is also radius, and here at the center we have a point charge capital Q, and this I have taken d theta here. The angle created at the center due to the small segment is d theta. but here I'll divide it as this side d theta by 2 and this side d theta by 2. So total angle is d theta. Okay. Now obviously we know that there is a tension, and that tension always acts tangentially. What is the direction of tension in the ring? Instead of tension, I'll call it as increase in the tension. I'll call it as dt. Increase in the tension, this side is dt along the tangent. Now similarly, increase in the tension at this side, this is also dt. This tension is acting at point A and this tension is acting at point B along the tangent. Okay. Now let us resolve this into two components, one along this direction and another along this direction. Similarly here also, one along this direction and another along this direction. You can split it. Now from the geometry it is clear that if it is d theta by 2, here also I can write d theta by 2 and this angle will be all again d theta. We can prove it, but as of now I don't want to go through that. Okay. Here what we got, d theta by 2 and this is also d theta by 2. Okay. Now I'll call this component as dt cos d theta by 2 and I'll call this component as dt sin d theta by 2. The same thing here also. This is sine component. Okay. And here you have dt d theta by 2. Okay. Now apart from this, as you have placed a point charge q at the center and here you have a small amount of charge on the arc length AB. So obviously according to Coulomb's law, there should be a repulsive force between these two charges, and let us say that repulsive force acts here. I'll call this force as dF. dF is the electrostatic repulsive force acting on the arc length AB of charge dq. Okay. Now let us write the condition for equilibrium. Okay. In spite of all these forces, the ring is assumed to be at rest. That is possible only when the net downward force cancels with upward force, and this component of force and this component of force will cancel each other, and we can equate net downward force equals to upward force. Okay. Let us write that one here. Condition for equilibrium of the ring, we have the net downward force is d. Okay, the net downward force is 2 dt sin d theta by 2 equals to the net upward force is electrostatic force. But as I have said, this angle d theta is very small. For small values of theta, for small values of d theta, we can write sin d theta by 2 is nearly, we can take this one, but we should measure the angle in radian. Okay. So therefore if I use in this above equation, if I use this one in the above equation, what I am going to get, 2 dt into d theta by 2 equals to df. Now you can cancel these two. The remaining part of the equation is dt into d theta should be equals to df, and I'll call this as equation number 1. Before that, I'll introduce one more concept called linear charge density. Total charge on the ring is q and total length of the ring is 2 pi r, that is length of the circumference. This is also equals to charge on the small part of the ring upon length of the small part AB. Okay, this can also be written as, the length AB can also be written as r d theta. How we got this one? Because because angle created at the center is equals to arc length by radius. Therefore AB equals to what? R d theta. Now from this equation you take this part here, this side, so that I am going to get an expression for dq d cube equals to q by 2 pi r into r d theta. You can cancel this r, the remaining thing, into d theta. I'll call it as equation number 2. Take a look on this. The small amount of charge on the small segment of the ring, that is dq equals to this much. I'll call it as equation number 2. Okay. Electrostatic repulsive force according to Coulomb's law, we can write it as k capital Q into dq by, what is the distance between them? R square, radius. Okay. This can also be written as k capital Q by r square into the value of dq. From equation number 2, I'll take the value of dq, where the value of dq is dq equals to q into d theta by 2 pi. Okay. I'll call it as equation number 3. Therefore, from equation number 1 and 3, we have what you can write, dt into d theta should be equals to pi. Now simplify this equation. Here you can cancel this term. What is the remaining thing left? Okay, let us write it here. dt equals to k small q into capital Q by 2 pi r square. So this is the answer for the first question. So everywhere inside the ring, this much of increment will be there. This is the increase in the tension. Now let us go through the second question. What they are asking in the second question. Okay, let us try to figure out. Let us say this is half part of the ring and positive charge is put on this. This is positive charge, and let us say here we have, okay, this is radius. Now they are asking, on this half part of the ring, what is the force acting? How much force is acting here? They are asking. What is dF equals to? Okay, and here the tangential component acting downward is dtt. Here also it is dt. Under the action of all these forces, this is part B. Under the action of all these forces, the ring is at rest, means the ring is in equilibrium. That is possible only when the net downward force should be equals to upward force. So that the force, the electrostatic force acting on the ring, that is dF equals to 2 dt. Now I can take the value of dt from the equation number 4. What is that? Okay, you can cancel this term. So finally, the force acting on the one of the part of the ring I'll call it as equation number 5. You can see it. Please take a look on this. So this will be the force acting on this semicircular part of the ring due to other. Okay. Now in the third part they are asking that what is the force exerted by this point charge on the half part of the ring. Okay, I have taken half part and here it is radius r. Okay, half part of the ring. How much force is acting here? dF. Let us calculate. Okay, dF equals to k q by pi r square. So this is the answer. I'll call it equation 6. Okay, already we have calculated this one in the second part. So answer for the third part is same as that of the second part. You can think over this why the answer is same.